It's always the same spot, 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 all the way along. All right. Now, on top of that, I get an interference pattern. Whatever. So I get an interference pattern. And both of them happen at the same time, and here's what happens in nature. Do I have a bright from interference and diffraction at this place? The chop means bright, right? So this is a bright interference, this is a bright diffraction. So yes, I see this, yes, I see this. Yes, 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 no, no, yes, yes, no, yes, yes, no. Do you see it now? So whenever one or the other is a zero, there's nothing. Even if the other one would have been there, if one of the others is zero at that point, it cancels it. So I meant to make those x's, not pluses. So these are canceled because the diffraction doesn't allow it. All right? And these are canceled because the interference doesn't allow it. Right? So the diffraction would be that wide, but the interference kills it at these locations. So if one or the other cancels, it cancels it for the whole thing. Because 0 times anything is 0. Yes?
What's being canceled?
The light, the intensity of the light. Which, when I said that, reminded me of something I wanted to say here, back. The thin film coating they often put on camera lenses, in addition to preventing glare, which is helpful for people who are taking pictures for National Enquirer, if people don't see the sun reflecting off your lens. But what else does it do? If you don't let light reflect, and light is energy, and energy can't disappear, what did it do instead?
Yeah.
It went in. And that means it's easier to take a picture. You get more light on your film. You don't have to take as long an exposure. Does that make sense? So you can't cancel without it showing up somewhere. So it turns out that when we have the interference pattern, the dark spots actually make the bright spots brighter because the light had to be somewhere. All right. So the total intensity across there still adds up to the total amount that would have been there from the diffraction pattern. It just means we get brighter spots on the interference. Okay, so I do realize that I use a lot of words that have special meaning that you're still trying to wrap your brains around, but hopefully that will help you a little bit with some of the homework. From there, I want to move on just briefly to another basic idea. So there isn't much more new material before we have our final. So I've got today and Wednesday where I'm going to introduce a little bit of new material. And part of what I want to talk about today is the idea of polarization. I don't maybe I'll first look that up. So it turns out when light gets made, there's a very interesting thing, and we haven't talked a whole lot about that in this class, but remember we talked about electric fields, right? Magnetic fields below these many weeks ago, and you completely wiped it out because we already took that test and who cares. But you remember I talked about the fact that the electric field basically is a vector, and if I have a light wave, what's interesting is I have a changing electric field. So the electric field grows, becomes big, then shrinks, and then becomes negative, and then so it's doing this constantly, which is what gives the idea of a wave. But it turns out the magnetic field perpendicular to that is basically doing the same thing. So if I can do it, what's basically happening is that you've got them both going in opposite directions and oscillating back and forth, recreating each other, and that defines the direction of propagation of light. But light's made randomly, so some are doing this and some are doing this, and I mean things are oscillating in every possible direction. All right. Polarization says, let's take it and force all the light to go away except for the light that's doing this. Right? The problem that you get with that is that if I have a light ray that's doing this, that's fine. But if I have a light ray that's doing this, it turns out the electric field is a vector. And as such, it has a component in this direction and it has a component in this direction. This component is along that line, so it survives. The only thing that doesn't survive at all is something that's doing this. If I make it go through a polarizing filter that's oriented like this, things oscillating this way, it can't get through. You got the basic idea of that then? So polarizing basically is we're only to keep the vector components that are going this way. So hopefully that'll make it a little easier to see what I'm about to show you.
So what happens to the magnetic field?
It does the same thing.
Okay.
So, but just at 90 degrees. All right, so these are polarizing filters. All right, so basically hopefully everybody can see, I mean, you can see through it, right? The light's cut back a little, but you can still see my hand through it just fine. What happens when light passes through this, you can tell there's less light coming through, and that's because it's cut out all the light that was, so we've got an axis, only the rays that are going this direction make it through. All right? But every ray that isn't going this direction has at least a little part of it that comes through. And I'll do the math here in a second, but I first want to get, so you can see my hand there. All right, but if I take this one, again, you can see my hand behind there. If I take this, and you have the light coming through, and I put this in front of it, when I rotate this to be perpendicular, if all the light's going this way, and then I have this one in this direction, it only wants light going this direction. So what happens is, watch as I rotate that, and hopefully we can see. All right, so what happens is that when they get exactly 90 degrees off, nothing gets through. But life is weird. If I now take, well, first off, let me put this in, nothing happens. But watch what happens when I put this in between. I put it this way, nothing, but when I begin to rotate it, can you all see that okay? By putting it in between, now you can see through it again. Because nothing's exactly 90 degrees. I put it at 45, so there's a 45 between the first filter and this, and then there's another 45, so nothing ever completely cancels. Because you need 90 degrees to completely cancel. It's pretty cool. All right. Yeah. So what? And we'll talk a lot more about this on Wednesday, but because I only have one day to finish everything, I want to get this idea basically out there. So the idea is that we talked about radius scattering, making the sky blue and all that. But what I didn't tell you is that it also turns out that when the light scatters off the nitrogen in the atmosphere, it actually polarizes it. So that if you were to hold this up to the sky and look and rotate this while looking at the sky, the color of the sky changes. This is actually also then part of what's used in some sunglasses, is that they take advantage of putting axes that are, generally what they do is they try to put the polarization axis up like this, because the scattering effect, especially like off roads, car hoods, water, it tends to polarize like this. Then by doing this, you'll cut down glare, all right? Because it's 90 degrees. And then it also eliminates glare from the sky. Fishermen will also use glasses, because sometimes if you're looking for fish, but there's light reflecting off the surface of the water, if you put on polarizing glasses, it cuts it so the reflection doesn't get through. You can see straight through the water to see what the fish are. So this idea is used quite a bit. So, and I think I mentioned this, but just to make it a little clear. So this polarization thing helps cut down on glare. It's a very useful thing when driving. And so people used to wear polarizing glasses when they were driving to be able to cut down the glare on the road and everything. And then it became such a safety thing that they decided to just go ahead and polarize the windshields of cars. The problem is, that works if you're sitting this way and the windshield, but if you tilt your head, suddenly the world disappears. And it was not safe. So now they only partially polarize the windscreens.
How come window tint looks weird when you're wearing polarized glasses?
Again, there's always an element of polarization going through, and so polarization often, what it does is it favors certain colors of being canceled.
I'll give like reflections.
Yeah, so like, and I've never seen what you're referring to, but I'm imagining it's a combination effect of some colors being canceled and others not, and two polarizing fields not quite at the same angle as you might have expected. All right, so the next thing with that is, so we looked, I'm going to give the equation. Thank goodness the equations are relatively easy. All right. So the first thing is, if you have unpolarized light coming through a polarized filter, half the intensity of the light is canceled. So what we say is the intensity you get is 1/2 the initial intensity. So we use I for intensity. All right. So the intensity of the energy is 1/2 of unpolarized light through a filter. Can't read that myself. All right, so we have unpolarized light going through a filter. That's the first equation. Then, after that, once I know that light is polarized in a certain degree, at a certain angle, if I take the filter and I rotate it, so this is called the axis of the filter. If I take that and rotate it so that the axis is at an angle compared to the polarization, then the amount of light I get is something we do by Malice's law. And it says that I is equal to I naught cosine squared theta, where theta is the angle between polarized light and the transmission axis. Often referred to as theta TA. Let's put that so it's not just mapping. So I do this. How much light, what happens through the first filter? Do I need to worry about any angles at all? No. But as soon as I'm holding this up, what have I established mathematically? My TA, my transmission axis. Anything that comes through is going to be polarized this direction. That's my transmission axis. Take my second filter and I put it up. Now what determines how much gets through that filter is the angle between those two. This is my transmission axis. Whatever the angle of this one is, that's the theta that goes into this equation right here. The angle between the transmission axis and the other filter. So let's say this is a 45-degree angle. Right? Let's say this is a 45-degree angle. How much of the totally unpolarized light that lands here makes it through the second filter? So I got through two filters. How much makes it through the second filter?
A quarter.
No. Let's be careful. How much makes it through the first filter? 1/2.
Yes.
Right? The first filter. Remember, unpolarized light always gets diminished by 1/2 through the first filter. Now, how much makes it through the second filter? So I come here and I say, all right, my intensity I'm getting is the amount hitting the second filter, which I know is actually 1/2. This I know and this I know are not the same. This is the amount that hit the filter, which is 1/2 of what I started with. Yes? First filter. Right? Second filter. This is my incidence. That's what hits the second filter. And then I multiply by the cosine squared of 45 degrees. Because I told you it was an angle of 45. Does anybody happen to know what this cosine of 45 is in numbers?
1 over root 2.
Root 2 over 2, right? So cosine 45 equals square root of 2 over 2. What happens when I square that? What's the square of square root of 2?
1 over 2.
All right, so it becomes 2 over 4 equals 1/2. So my final answer here is equal to 1/4. Because it's 1/2 times 1/2. So it's 1/4 of the initial intensity. All right, so got 1/2 of the initial intensity from the first filter times cosine squared of 45, which is just 1/2. So 1/2 times the 1/2 gives me the 1/4, and I still have my whatever my original intensity was. All right. So in all the problems that they deal with, they basically use this idea. There is one silly thing that they do, which I'm not sure why, because I couldn't find it anywhere in our textbook. This comes from their borrowing. If in one of your homework problems you run into the word tourmaline, which is a gem, translate that to be polarizing filter. Because tourmaline is a polarizing filter. So don't worry about any other properties. When they say tourmaline, just think polarizing filter. All right? So it's just that they could have said, you have a polarizing filter, blah, 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 blah happens. All right? And then the last thing, and I'll do more of this on Wednesday, but in case somebody's actually trying to get a head start on their homework. If I have a 100-watt bulb, what does that tell me about the amount of light coming out of that bulb? How much energy is there? Okay, so at what rate is energy leaving this bulb?
100 joules per second.
100 joules per second. That's what that means, right? 100-watt bulb means 100 joules per second. All right, so I put that bulb in a little box, and the question I have is, how much energy per second is hitting the box?
100 joules per second.
It's still 100 joules per second. Now I put it in the room instead of the box. How much is hitting the walls, floor, ceiling? 100 joules per second. Doesn't matter how big it is. Are you with me? So if you have, and they have several situations, they say, I think they actually use a 40-watt bulb, and you're looking at a sphere with a radius of 3 meters, and they ask you to find the intensity on the sphere. Intensity is defined to be the power, or the total power over the surface area. So in this case, it's It's really easy. What's the power? It's what you pay for, so 40 watts. All right? It's 40 watts, and it lands over the surface area. Do you know what the surface area of a sphere is?
4 pi r squared.
It's 4 pi r squared. So in this case, I would plug in 3, and it literally just becomes calculator problem now. It's 40 watts divided by 4 pi 3 squared, or whatever thing they give you. And that gives you the intensity at the surface of the sphere. If I put a polarizing filter, just in front of the sphere, so this light is radiated, and now I grab one of these, and it's the edge of it, and I put it right here, how much, what's the intensity at the sphere behind the polarizing filter? The same, exactly. So if I know what it is for the rest of it, it's 1/2, because what did this do? It cut the intensity down by 1/2 by definition. Are you with me? Cool, all right. So I will promise we'll go over this again on Wednesday, but I want to get some of these seats planned because Wednesday is my last day to talk about this, and then Friday we review for the test. So I want to be sure that you get a jolt that says, yes, vacation is over.
Are we getting the practice?
I basically gave the list of what to study, right, last time? I'm trying to wean you off of practice tests and that saying, I'm telling you what to look at and be very specific what problems you need to do, but yeah, you can talk about more about that on Wednesday. So yeah, I gave a really specific list I thought last time, things you needed to study. I'll think about it. I don't want to do quite such detailed thinking. I mean, there are no surprises. I already told you what questions to know how to do. But the H section is the only thing I haven't covered yet. We'll do that on Wednesday. Oh, yeah.